In this video, I introduce the design of a probability density path in flow matching. Diffusion models learn to map from a Gaussian distribution pi0 to a target distribution pi1. However, diffusion models often come with a high computational cost during training and inference. Flow matching learns the mappings via a stochastic process that transforms from pi0 to pi1 through an ordinary differential equation. A training dataset Sn comes from an underlying continuous time dynamical system. Xti is the observed state of a ground truth system at arbitrary time points ti. To predict the distribution of the oncoming error elements given the first key elements, as shown here. The FM model uses the probability density path to model one-step predictive conditional distribution. A pre-trained encoder E maps X in data space to Z in latent space. The FM model uses the distribution P to approximate the ground truth distribution Q. The latent dynamics can be modeled by ordinary differential equation as shown here, where ut is a vector field describing change of state at time t. A decoder D maps Z in latent space to X in data space, as shown here. Flow matching model uses the following ordinary differential equation, as shown here, to infer the dynamics of the system, where phi t is a time-dependent flow that pushes the reference distribution P0 towards the distribution P1 along some probability density path Pt and the corresponding vector field Vt, as shown here. The flow matching model learns a deterministic coupling between the P and Q by learning a vector field Vt, such that the solution to the ordinary differential equation above, as shown here, satisfy Z0 sums from P and Z1 sums from Q. When Z is the solution to the ordinary differential equation for a given function Vt, Z is the flow with the vector field Vt, and Z0, Z1 is the coupling of P and Q. Sampling from P, we can generate approximate samples from coupling by sampling Z0 from P and numerically integrating the ordinary differential equation that is viewed as a continuous normalizing flow. If Vt is modeled with your network Vt state, the least square regression is solved by minimizing the flow matching loss as shown here, where T sampled from a uniform distribution U, Z sampled from Pt, Wt is a weighting function. Since there is no prior knowledge to choose Pt and Ut, and there exist many choices that can satisfy P1 similar to Q distribution, a target probability path is constructed by mixing conditional probability paths as shown here, where P0 equal to P1 is a normal distribution for a small epsilon larger than 0. A marginal vector field Ut is computed by using this formulation, where Ut is a conditional vector field given a pre-trained, predefined probability path Pt and corresponding vector field Ut. The CFM loss is minimized by using this equation, this prediction, and this target that is used to train the network Vt set. Where T sampled from a uniform distribution U, Z tilde sampled from Q, Z sampled from PT, and UT is a vector field defined per sample. Z tilde, that generates the conditional probability path PT. Setting Z tilde Gaussian probability path are defined as here, where AT is equal to 1 minus T, BT is equal to T and CT are differential time-dependent functions on 0 and 1, and I denotes the identity. There are many choices of vector fields that generate a given probability path. However, the simplest a vector field that generates a flow whose map is affine linear, as shown here. For a Gaussian probability path above, consider flow map psi t with ct larger than 0, the unique vector field that defines psi t is shown here, where the prime denotes the derivative with respect to t, and ut generates the Gaussian path pt. The conditional loss is defined as here, where t sampled from the uniform distribution U, Z sampled from PT, and Z sampled from Q. For more details, please check with these references. Thank you. Bye.